All right. Next would be short fibers, which the aspect ratio here may be 100 or so. So the length of the fiber is about 100 times the diameter of the fiber, would be an appropriate classification for short fibers. Particulates, flakes and whiskers, these are kind of getting into the zero-dimensional type reinforcement, right? Where the aspect ratio is about 1, same in all sort of directions. Particulates, whiskers, flakes, generally smaller with an aspect ratio of about 1. Okay. We classify matrix materials for composites usually by the type of matrix material that it is, whether it's polymer, ceramic, or metal. So if you had your material science class, you probably spent a lot of time talking about metals and ceramics and polymers sort of separately. And that's because generally polymers have same or similar behavior, and that behavior is markedly different from metals, and that behavior is markedly different from ceramics. Okay, so we're going to do the same when we talk about our high performance aerospace grade materials as well. And thank you, whoever started the recording. Good job. You get A for the day. All right. 1,000 Dr. Hart points redeemable for absolutely nothing. Okay. Now, the matrix materials we're going to classify according to their temperature and the surface temperature that they're capable of withstanding. So when you're talking about polymer matrix composites, usually the surface temperature is no more than 200 C. There are some polymers that can handle higher temperatures, specifically imide classification polymers, but most polymers that you're familiar with, your thermoplastic, ABS, polypropylene, high-density polyethylene, or your thermoset polymers like epoxy and any cross-length material that you can think of, those are going to be probably 200 C or less. Okay. Metal matrices, depending on the metal, surface temperature and continuous range of 800 C or less. So now we're getting into aluminum, brass, etc. Most of those metals start to melt or soften around 1,000 C or more. So you're talking about a continuous surface temperature of 800 C or less is probably appropriate. Ceramic matrices, those are the best by far for temperature performance, but we know ceramics generally are brittle, so maybe not the most appropriate choice for matrix material unless you know you're not going to have a lot of potential for fracture. All right, so as I just mentioned, our matrix materials are going to be classified by their surface temperature, that's service, not surface. And here's kind of a sort of a one-dimensional temperature chart that shows these various surface temperatures. And what is the purpose of the matrix phase? So this is an important takeaway for this particular class. What does the matrix do? What is the purpose of the matrix in the composite? Well, reinforcements by themselves, like glass fabric on its own, glass fibers on its own, don't really have a lot of load carrying capability and compression, right? You ever put your cloth of your shirt into compression? It just buckles, right? We know that. And I have some example glass fibers here that are not infused with polymer that we can sort of take a look at. So I'll try to put a little bit of this on camera. So here, this is a glass fabric, very thin woven glass fabric mat, and by itself it just like doesn't take any load. I can compress this thing. It just feels like the cloth of my shirt. If people in the class want to maybe pass this around, be careful with COVID and whatnot. You can sort of pull stuff out and take a look and feel for yourself. But those are glass fiber reinforcement materials that might make up a composite. And those by themselves don't really have a lot of load carrying capability. So one thing that the matrix does is it gives a binding for all the reinforcement so that the reinforcement can share load and also sort of go into compression, right? It's not going to buckle because it's surrounded by polymeric or metal or ceramic material. All right. So another thing that's a little bit more subtle is that the matrix protects the fibers. When you're talking about, ceramic fibers like glass is particularly prone to fracture, which we know. So you need a more tough material to protect that glass so that it doesn't fracture. So the matrix helps you with increasing the toughness generally of the reinforcement. So that's another thing that the matrix can do. And also, the matrix materials generally are more chemically resistant than the fibers. That's not always the case. If you have a glass fiber composite, glass generally is very chemically inert and resistant. But carbon is one of the most reactive elements on Earth, okay? So if you have a carbon fiber composite, you need matrix material so that the carbon inside of the carbon fiber isn't reacting with the environment around it. So if you ever try to use a carbon fiber material in an aqueous environment or somewhere with a lot of humidity, you could be in for some problems if your matrix isn't protecting you properly. So the matrix allows load sharing, it allows increases in toughness and protects the fibers, and it also gives chemical resistance to the fibers as well. All right. So let's dive into each of the matrix types. First, we'll talk about its polymer matrices, and I'd say a majority of composites that are used in the world are polymer matrix composites. So when you think about high technology sectors, usually polymer matrix composites. And you can sort of classify the polymeric matrices into two different categories, thermosets and thermoplastics. Now, I think you guys talked about thermosets and thermoplastics in material science classes. Yeah, okay. So generally,
Yep.
I think we're kind of aware of the differences between thermoplastics and thermosets. Am I losing you guys here? No, it's okay. I think my connection was a little weak there for a second. But I think generally you guys understand the difference between thermoplastics and thermosets. Thermoplastics are able to be molded and remolded and recycled just by application of heat. When you heat them up, they will flow. You can recycle them over and over. So if you raise the temperature of a thermoplastic, it will melt and you can reform it, right? That's different than a thermoset. A thermoset is like a cross-linking reaction that is more or less permanent, okay? There's no reheating a thermoset material to recycle that material. So think about a two-part epoxy that you might mix together to fix something at home. Okay, you mix part A and part B together. You've initiated a chemical cross-linking reaction which cannot be undone. Right? So it will proceed with its reaction, and even if you then heat up that thermoset material, it's not going to melt, it's not going to reform, it's just going to eventually combust and burn into flames. All right, so it's never really going to go back into that liquid form ever again once you've mixed it. So that's what we're kind of trying to show with these time graphs here in the upper right corner, is that as time goes on, you can raise the temperature of a thermoset all you want, the viscosity, quote unquote, the solidification, is never going to go back down. However, with thermoplastics, you can heat these things up with temperature and it will soften the material. And then if you cool it down, it will reharden. Okay, so it's like reversible or recyclable kind of idea, right? So some examples of these particular materials, thermosets might be polyesters, or epoxies are probably the biggest one for this particular class, polyimides, etc. Irreversible chemical reaction and remain solid. Thermoplastics, some common examples, just think your commodity polymers. PEEK, polypropylene, PES, PMA, PMMA, PLA, all these ABS, 3D printing plastics are all basically thermoplastics. Okay, so they're recyclable and they undergo sort of can be recycled with heat. Let's dive in a little bit more on thermosets. I'm not going to dive too much into chemistry in this particular class, but if you take the advanced composites course, we talk quite a bit about chemistry and cure kinetics, especially of thermosetting resins. But thermosetting resins, the ones that go irreversible chemical reactions, usually are made up of polymer networks. And I have an example of a reaction of an epoxy and reacting with an amine here, and it's a little sort of complicated, but more or less this epoxide ring, which is this three-membered carbon-carbon-oxygen triangle, is under quite a bit of strain. If you remember from your chemistry classes, three molecules in a triangle together are under quite a bit of strain. Okay, generally you want like 6 molecules in a ring for them to be comfortable. Okay, so if you're thinking of your phenyl group, which is like a group of 6 carbons in this general-looking benzene ring, those molecules are comfortable. But 2 carbons and an oxygen kind of all bonded together, they're very uncomfortable. They're under a lot of strain. So what happens is that triangle wants to sort of spring open and react. So what happens is we grab an extra hydrogen from this amine and it pops onto this epoxide group and this becomes an OH group. All right, so we see a lot of these strangling OH groups. All these OH groups here in the reactant side, they're coming from this triangle where the O has popped open and received a hydrogen. Okay, this is what's initiating the cross-linking and creating you your irreversible chemical reaction, which is giving you your thermoset. All right. Now, the properties of your thermosets generally depend on the density of the crosslinks, and the density of the crosslinks depends on sort of the backbone of each one of the molecules that makes up the epoxy. All right, so you can have a lot of different molecules that make up sort of the backbone of these epoxies, and that's why you have 1,000 different types of epoxies. All right, so there are many, many different varieties of epoxy, some with cure times of 2 minutes, some with cure times of 2 days at room temperature. Okay, so a lot of properties of these thermosetting materials depend on sort of the backbones of these epoxide and amine moieties. All right. So 2 components, irreversible cure, we've said that quite a bit. And because these go into this cross-linked reaction, this backbone is actually quite brittle. So if you think of like a glassy cross-linked sort of structure, that ends up giving you this epoxy material which is like very hard and very stiff, but also quite brittle. So I have an example of pure epoxy here. I can show you this. Don't worry about the general geometry for this guy, but this is a pure epoxy material. And I can sort of knock on it. Can I get close to the mic? I gotta like get close to the mic. Okay, it's like very hard, and you can see it's got this sort of amber color. This epoxy here is like a 24-hour cure epoxy at room temperature, and it gives you this general, like hardened, very stiff, modulus of about 2 GPa kind of material. So I'll pass this around. You can sort of feel what this epoxy sort of generally looks like. Please don't break that. No dropping, okay? You would get the idea if you held it in your hand that it's very glassy, and if you dropped it from about chest height, it would shatter on the ground. Okay, so please don't do that. Don't do that. Okay. There you go. So sorry for those of you that aren't here in person. I'll bring those. Yeah, Alex says in the chat he's going to try not to drop it. Okay, good. Thanks, Alex. I'll bring those samples again next week so you guys can see them. These thermosets, their general cure cycle looks something like what you have on the right-hand side. So if we're looking at the viscosity of this material as a function of time, when you mix part A and part B, there's going to be a chemical reaction that happens to sort of harden this material and bring the viscosity of the 2 liquids to infinity, all right, giving you a solid product, right? Now, as we increase the temperature of the reaction of these cross-linked materials, that reaction will proceed more quickly. So what you see kind of in the graph here in the upper right-hand side is, let's say we mix this material at time t0. If the temperature is low, the viscosity will lower initially because it's heating up, because it's a chemical exothermic reaction, and then it will eventually sort of shoot off to infinity here as it begins to harden and create your solid product. If we increase the temperature, the character of the curve basically looks the same, except it's just sort of shifted by a multiple here of maybe 2, it looks like, by the graph, right? So what's happening there is you got these liquid components, and they're all mingling together in this liquid space, and they will eventually sort of cross-link with each other and turn into this gel material, and then eventually they'll have this glassy sort of behavior as all the cross-links sort of form and come together, and they've all mingled together, okay? So the amount of time that it takes to sort of go from your liquid components to a semi-solid state where you can no longer like manufacture with that particular piece anymore is what we call the gel time, or the pot life, or the working time. So if you're like interested in how much time do I have to manufacture my composite with this particular epoxy, a lot of times you'll go to a data sheet, and you'll see on the data sheet some listed number that says pot life is 2 hours at room temperature, okay? And that is more or less the amount of time that you have to work with that liquid epoxy before its viscosity is too high to continue the manufacturing process, right? So when you see those sorts of terms, pot life, gel time, etc., that just gives you an indication of how much manufacturing time you have before you can't really work with that cross-linking polymer any longer. So here's some real-life data taken with an instrument known as a rheometer. And what you're looking at here are 3 different lines. The blue line is the viscosity of the liquid as a function of time. So what we're doing in this experiment is we put liquid between 2 plates, 2 circular plates, and we oscillate those plates back and forth, and the amount of torque required to oscillate those plates back and forth gives you information about the viscosity of that particular material. So you can track that with a scientific instrument known as a rheometer, and that's what we're tracking here. We're tracking not only the viscosity, but the stiffness. So when you see those parameters there, the moduli, the red and the black curves, that's the stiffness of the material as a function of time. So we see this particular resin at time t0. It starts with a viscosity of more or less 0, so think water-like or very similar to water. And then over time, it becomes more and more and more viscous. I'd say here at about the 400-minute mark, we're probably approaching a situation where we're at like a point of no return, where we're probably not going to be able to manufacture much anymore after this. Viscosity rising, and then you see right at about the 600-minute mark, this thing really just takes off. So I'd say you could probably get away with maybe 360 minutes of working time for this resin. It's maybe 6 hours is probably appropriate. And you're probably fully solidified 12 hours, right? So this actual real-life data was taken with this particular epoxy resin system, Araldite Aradur 8605, my favorite type, okay? And this was done at room temperature, all right? So you can see the stiffness evolution of this over time and how that kind of goes. And you can also see how the viscosity evolves and sort of shoots up to infinity as we sort of let this progress at room temperature. All right, so real life data. Yes, show me the data. Or the money. I forget. Which one is it? I don't know. Been a while since I've seen Jerry Maguire. All right, leave me alone. All right, continuing. The advantages and disadvantages of thermosets. All right, so thermosets have the advantage in that they're generally very strong and generally stronger than thermoplastics. Okay, and that's because this cross-link structure is just like very solid and very hard to break. Okay, also there tends to be stronger bonds between the matrix and the fiber when you have thermosetting resins. That's because you have a lot more chemical reactions going on between the epoxy and the fiber, a cross-linked material, than you might have with a thermoplastic material. Okay? Thermoplastics don't have a lot of affinity for chemical reaction with things like glass and carbon fiber. All right? But if you're talking about a liquid epoxy part A, liquid epoxy part B, there are a lot of chemical reactants in there that might chemically bond to the surface of a fiber. And so because of that, you end up with like very strong bonds between the fiber and the matrix when you're talking about thermoset plastic materials. All right? Continuing. The thermoset structure, this cross-link structure, also gives amazing chemical resistance. So if I take that epoxy piece over there and I drop it into acetone, it's fine. Okay, it would last in acetone for at least days, probably weeks. All right. If I dropped a piece of PLA into acetone, that thing ain't surviving weeks. Okay. So polylactide PLA, this is a thermoplastic material. If I drop that into acetone, it's going to be dissolved in probably a day. All right. So thermosets are much more chemically resistant than thermoplastics because of this cross-link structure that's hard to break. Right. So degradation from recycling, also not an issue. Thermoplastics, they can be reused over and over, and sometimes reusing thermoplastics over and over can lead to degradation of their performance. Okay, so if you remolded the same polymer over and over and over, talking about a thermoplastic now, you're probably going to lose some of the mechanical performance of that thermoplastic. All right. So some of the disadvantages, cure times may be long, and temperatures required to cure these thermosets may sometimes be high. Not all thermosetting reactions proceed well at room temperature. Sometimes you need additional activation energy, remember your chemistry classes, to sort of initiate the cross-linked chemical reaction required to make the thermosets. You can't recycle them, and generally, thermosets are more brittle than thermoplastics. So that's also a consideration. They're very glassy. They behave more like ceramics than they do like tough thermoplastic polymers. Okay, so there you go, advantages and disadvantages. Now, on to thermoplastics. Onward, I say. So thermoplastics are more your commodity polymers, like we said before. ABS, PLA, PEEK, etc. All right. Most of these are characterized by very long chained structures that have some unique aspect about them that makes it PLA or ABS or whatever. It's not really meant to be a discussion on various thermoplastic polymers. Just understand that they differ in structure from thermosets and that they don't have this like cross-linked sort of chemical structure, right? Because they don't have that cross-linked chemical structure, they can be recycled, right? So you can use them over and over and over, all right? Some commodity polymers you might be familiar with, polycarbonate, ABS. These would be amorphous thermoplastic polymers, but thermoplastics can also be semi-crystalline. You guys talk about semi-crystalline materials? Let me, you can get it. Okay, Jack's nodding yes. Okay, so they can be semi-crystalline or amorphous. And usually fabrication requires softening, melting by applying heat, and then molding them. Their properties are going to depend on crystallinity. The more crystalline they are, the stronger they will be, but the lower toughness they will be. The more closer you are to a crystal, the more closer you are to what is a thermosetting material. All right, more ductile than thermosets. Okay, if we think about the ductility of ABS versus the ductility of epoxy. It's much different behavior. Right? Generally lower maximum service temperatures than thermosets. All right, so thermosets can handle maybe up to 200 C. Thermoplastics, depending on the thermoplastic, they break down anywhere from 50 to 150 C probably. All right. So when you're talking about PLA melts around 50, 60 C. ABS will probably start to go around 180 C, something like that. So, yeah, keep that in mind if you're thinking about continuous service temperatures for your materials. All right. Your thermoplastic advantages and disadvantages. Advantages, you can melt and reform them. That is a nice advantage. They usually have shorter processing times. When you think of an injection molding process, which is just strictly a thermoplastic processing technique, usually injection molding processes take orders of minutes. All right? But if you're going to manufacture a composite with a thermosetting plastic like an epoxy, your manufacturing time is probably not going to be order of minutes. It's probably going to be order of hours or longer. Okay? So the manufacturing times, if you're using a thermoplastic, much shorter. And generally, these thermoplastics are tougher, so they have higher impact resistance. So if you are afraid of bird strikes, for instance, if you're flying an airplane, or you're designing a vehicle and you need energy absorption for your nose cone, all right, maybe it's better to consider thermoplastic materials rather than thermosetting materials because they're generally tougher and absorb more energy. Disadvantages, bad chemical resistance. We talked about this. If I dropped ABS and acetone, that thing would be dissolved. All right. Bonding with the fibers is difficult. There are typically no free reactive groups in thermosetting or thermoplastic materials that are there and available to react with the surface of a fiber. Meaning you're not going to have a lot of chemical reactions between a thermoplastic and a fiber. Okay, it just doesn't happen very often. So generally bonding with that fiber can be a problem. And if you're talking about load sharing to the fibers, that can be interrupted if you have a thermoplastic material. Okay. Lower maximum surface temperature and lower strength and stiffness generally than thermosets. So there you go. Some differences in your polymer matrices. Okay. Onwards to metals. Any questions about polymers before we move on? My polymer dance. Ooh. All right. Cool. Metal matrices. Metal matrices are rarely used. The reason being, the benefit that you generally think about when you think about composites is they are lighter weight than their other counterparts. Okay? So if you're going to make a composite that's a metal matrix composite, it's probably not going to be lighter weight than an analogous metal material. It'll probably be about equal or on par or somewhere close. So if you're going to use a metal matrix composite, you need to have very strong justification for why you're going to do so, because usually you don't get a lot of weight savings that you might get from your polymer matrix composites. Okay, so the advantages here: higher temperature range than composites. Okay, metals can stand 800 C, depending on the metal, sometimes even 1,000, sometimes more. If you make a tungsten composite, good luck processing that, but if you're able to make a tungsten matrix composite, you could probably do pretty well. All right, it's going to be heavy as all heck, but you'll have high thermal resistance. All right. Metals are generally more ductile. If you want to have some numbers to this, we talked about this last time, but an epoxy might have a toughness value of about 1. A metal might have a toughness value of about 50. All right, so it's about 50 times more impact resistant if you're talking about comparing, let's say, aluminum to epoxy. All right, so drastic differences in energy absorption. All right. Finally, if for some reason you need electrical or thermal conductivity, metals are significantly better than polymers. All right, the thermal conductivity of metals is tremendously higher than those of polymers. Polymers typically considered insulators. Metals typically considered conductors, both for thermal and electrical reasons. All right. So if you need electrical or thermal performance for whatever reason, maybe this is the way to go. Some disadvantages, however: difficult and expensive to process. It's really hard to make metal matrix composites. There's no way around it. You have to heat up the metal, which takes an immense amount of energy, into a liquid form, and then somehow inject it into a fabric or some other reinforcement that you need to use. All right, which is just not an easy process to do. So if you're going to use a metal matrix composite, you better have some good justification, because it's expensive to make, and they're usually not giving you a lot of weight savings. All right. Heavier than polymers, and again, difficult to bond metals to the reinforcement material. Okay, if I just take metal A and metal B and I sort of like mold them together, there's not a lot of general reason for them to chemically interact with each other. It doesn't really, you don't have a lot of chemical reaction usually. So the only bond you might have between like fibers and a matrix might be an adhesive bond, which generally is not great. Okay, so something to consider. All right. Now, metal matrices also have a restriction in that they will usually have a metal reinforcement or a ceramic reinforcement. That's because if you're talking about processing a metal composite, which might be 800C, 1000C to process it, then you need a fiber or you need a reinforcement phase that can withstand that processing temperature. Okay, so usually you'll have ceramic reinforcement inside of these metal matrices. Here's some examples, and these examples are showcasing what are some of the minor benefits of metal matrix composites, and that is their thermal performance. So here we have two different examples. One is an aluminum graphite particle composite piston and cylinder, and this was developed right up the road at UWM. And so what you're looking at here, this microstructure is graphite, so this is a sort of a carbon material, and it's embedded inside of a metal matrix. I'm not sure exactly what the metal is. I think it's aluminum, it says here, but not sure the alloy. But the idea here is that this piston needs to transfer heat quickly because it's heating up quickly in process. And so you have this thermal mass that is this piston heating up, and if it was made out of traditional polymer composites, it probably wouldn't be able to withstand the temperatures required of combustion inside of an engine. All right, so that's why you have this particular metal matrix composite taking advantage of the thermal properties of metals. All right, on the right-hand side, those are some brake rotors that are metal matrix composite, and so these are again useful for transferring heat away from the braking process. So there you go, metal matrix composite. All right. Lastly, of your matrix materials, the ceramic matrices. So ceramic matrices are useful in very niche applications where you're requiring high temperature resistance. So advantages here for ceramic matrix: high temperature resistance, high hardness and stiffness, low density, so they're on par, some of them, with the density of polymers, which is good. Low coefficient of thermal expansion, again, this is a thermal benefit. And really, really good chemical resistance, better than the thermosets generally. So if you compare chemical resistance of like epoxy to glass, which glass is a ceramic, the ceramic is going to blow it out of the water. All right, blew it out of the water. All right. The big advantage of the big disadvantage of ceramic matrices, holy moly, they're brittle. All right. So if you anticipate any sort of impact event or fracture or whatever, you're going to be in trouble. Um, this actually is the reason for Space Shuttle Columbia going down. Okay, one of the brittle panels on the space shuttle suffered from a foam strike on one of the wings that later caused it to sort of burn up on its reentry. So there you go. Ceramic matrix composites, very, very brittle. And while being chemically inert can be advantageous, so you're not going to break down, it can also be disadvantageous when you're talking about needing to react with the reinforcement to create a good bond. So that's also a consideration as well. All right, some common examples here on the bottom. Some carbides, so we have silicon carbide, titanium carbide, nitrides, this is silicon nitride, aluminum nitride, oxides, and all glasses that make up glass fiber composites would be sort of classified as ceramics. All right. Here's some images of ceramic matrix composites and where they might be useful. So the first obviously is a space shuttle. Space shuttle obviously is retired now, but when it was in production, they had a lot of ceramic matrix composites on the heat shielding surfaces for re-entry. And so this is a recovered heat shield piece that was taken after a thermal test. And you can see sort of the fibers here on the left-hand side that are kind of jetting out, this sort of darker color. Those are all the fibers that are kind of sticking out there, carbon fibers that would be. And then this sort of lightened material is the ceramic itself, and I imagine this darker portion is the ceramic that was in the high temperature. All right. So there you go. Also, jet engine blades are sometimes now made out of ceramic matrix composites, which is pretty awesome to think about. Like processing a jet engine turbine blade to be made out of ceramics, pretty kind of a feat of engineering, if you ask me, right? So very high thermal resistance and can withstand the temperatures of a jet engine. So there There you go. GE uses them. Here's a list of your properties. A couple, I just like put numbers up here for comparison, but we can kind of like look at some of these things. So if we think first about like polymers, tensile strength in the 50 MPa range. I mean, you might compare that to metals, where it's very similar strength values. All right, so aluminum, copper, nickel, roughly in the 50 MPa range. So for yielding, so similar like strength performance. All right, generally the stiffnesses are going to be lower. Here we're showing flexural modulus on the 1 to 30 GPa, where metals, their tensile modulus tends to be anywhere from 70 to 200. 200 for steel, 70 for aluminum GPa. Right? Where you see the big differences is the densities. Right? So the density of epoxy, polyimide, phenolics, these thermosets, in the 1 to 2 grams per cubic centimeter. Right? Metals much higher. So copper, nickel, maybe 4 times that, 5 times that of these thermosets. So you're seeing the trade-off in densities and in weights when you're talking about going from metals to polymers. All right. I think we'll stop it here today. I want to take the time to go through reinforcements all in one day. So we'll stop lecture here. For people that are in class, I have some more samples up here if you want to come take a look. For those of you online, I don't know if you have any questions, but that'll be it for today. We'll kind of cut it a little bit short today. And we'll pick up on the reinforcement materials starting on Monday. Have a good weekend. Rawr.